So let me share the screen. So now I hope you see my screen.
Yes, we can see your screen.
My aim in this lecture is to finish considerations of random dynamical systems for homeomorphisms generated by stochastic differential equation, and also to look at stochastic flows that are not flows of solutions of stochastic differential equations.
Georgi, can you make the full screen?
The full screen. It is the full screen, no?
I mean in PDF, in the PDF reader.
Okay, 1 second.
Okay, if it is complicated, don't do it.
Okay. Is it better now?
Yes, thank you.
So I will remind what we did yesterday. We constructed a flow of homeomorphisms of the Euclidean space that consist of solutions to a stochastic differential equation. dxt equals axt dt plus bxt dwt with Lipschitz coefficients a and b. Then we considered the shift of the Brownian motion. Now I will denote it by theta v of w. Okay, so this is the shift of a trajectory of w by v. And we did a simple transformation of the equation for phi, just shifting bounds of integrals. And looking at the second expression, where we have the stochastic integral with respect to the shifted Brownian motion, and knowing the uniqueness of a solution to stochastic differential equation, we can deduce that the process phi s t plus v of x when t is greater than s minus v is a solution to this stochastic differential equation. Hence, it must be indistinguishable from the unique solution to this equation, which we denote by phi. Now it will be s minus vt, but this flow phi will be constructed by the shifted Brownian motion. If we assume that we have more than just indistinguishability, if we assume that actually these processes are equal for all realizations of W, for all shifts, for all time and for all x, then we get what is called a perfect cocycle property. So assume that we have this equality, then simply because the mapping phi evaluated by shifted Brownian motion is phi s plus t, we get such such equality that the mapping over the time s plus t evaluated by W equals the composition of the mapping from time 0 to s evaluated by W and the mapping from 0 to t but evaluated on the shifted trajectory of W. When we have this equality, we get more understanding in the structure of random mappings phi st. In fact, we have not two parametric family of mappings, but we have a one parametric family of mappings. However, in the flow property, in the mapping phi t, we need to substitute not Brownian motion, but a shifted Brownian motion, which corresponds to the fact that when mapping acts from time 0 to s, the Brownian motion also moved in time. Okay, and such relations appear in the context of random dynamical systems. I recall the definition from yesterday. So in a random dynamical system, we have a probability space, a measurable group of measure-preserving transformations. Okay, measurable group means that theta h acts on omega, and it is measurable in two variables, in h and in omega. And a random dynamical system is a metric dynamical system and a measurable mapping phi. It has its arguments are the time, the randomness omega, and the state variable. And this measurable mapping satisfies the perfect cocycle property. So the mapping corresponding to time t plus s is equal to the composition of mappings corresponding to time to times t and s. However, here we need to shift the randomness by s in time. The theory of stochastic differential equations does not give us perfect cocycles. It gives us the so-called crude cocycles in the sense that for every fixed s, this equality holds for almost all omega and for all t. So for each s, there is some negligible set of omega such that for all omega not in this set, for all t we have the cocycle property. Of course, it is better to have a perfect cocycle property because a perfect cocycle immediately produces a flow of mappings. In fact, this expression defines a flow phi. Indeed, if we consider the composition of two mappings phi st and phi rs, okay, then we use their definitions, and we can write theta s omega as the shift by s minus r of theta r omega. Okay, and then we use the perfect cocycle property with omega replaced by theta r of omega. Hence, we get indeed the flow property for phi. So the composition of phi rs and phi st equals to phi rt. Okay, and let's look at a very simple example where a stochastic differential equation actually gives the perfect co-cycle. So this is the equation for the Ornstein-Uhlenbeck process. Lambda is bigger than 0, and we consider the stochastic differential equation dxt equals to minus lambda xt dt plus dwt, where w is the Brownian motion. Let's consider it on the classical Wiener space. So the probability space is the space of continuous functions with a cylindrical sigma field and Wiener measure. On this space, we have a shift that preserves the Wiener measure. Moreover, now this shift, it is even continuous in H and the W. So it is indeed, it is a measurable group of measure preserving transformations. Now the equation can be solved explicitly. Here is the solution of this equation. We know that there are some issues with stochastic integrals, that they are not defined pathwise, but in this example, the integrand is actually absolutely continuous, so we can understand this stochastic integral as a pathwise integral after integration by parts. So we get the family of solutions to this equation in the following form. And in fact, this function phi, yes, that depends on t, w, and x, it is a perfect cocycle over the shift. Let's check this. So what is phi of t, then the shifted Brownian motion, and x. So this is E minus lambda tx plus the shift ws plus t minus ws and minus lambda, the integral from 0 to t, E minus lambda t minus r. And here we have the shifted Brownian motion. So wr plus s minus ws dr. Okay, and we can transform it as follows. So it will be E minus lambda tx plus ws plus t minus ws. In the integral, we change bounds, so it will be minus lambda integral from s to s plus t E minus lambda t plus s minus r wr dr. Okay, and the integral with the ws, we can just compute it, and it will give us exactly ws minus ws E minus lambda t. So this cancels. Okay, and now if we substitute instead of x, instead of x, we substitute phi s wx, which is equal to e minus lambda sx plus e plus ws minus lambda integral from 0 to s, e minus lambda s minus r wr dr. So when we substitute this instead of x, what we will have, ws exponent will cancel, and this integral will be multiplied by e minus lambda t, so it will combine with this integral and gives integral from 0 to s plus t. So at the end we will get phi s plus t of x. Okay, so in this example, explicit solutions are a perfect cocycle over shifts. Moreover, we can find the invariant measure for this random dynamical system, and this invariant measure is concentrated on the following random variable. Note that the stationary solution of the stochastic differential equation is just integral from minus infinity to t e minus lambda t minus r EWR, which now coincides with the random variable psi evaluated at the shifted trajectory of W. Such random variables are called stationary points for the random dynamical system. So in this example, we can find the stationary point, we can find the invariant measure, which is actually concentrated on this stationary point, and also observe that the distribution of the stationary point is normal with mean 0 and variance 1 over 2 lambda, if I'm not mistaken. And this is exactly the stationary distribution for the Kolmogorov equation associated to the stochastic differential equation. And it turns out that actually all stochastic differential equations with the smooth enough coefficients, they give rise to random dynamical systems. This is a consequence of so-called perfection theorems. I will show you one of such results. So this is one of the first perfection theorems, which was proved by Arnold and Shoitsu. And the essence of the theorem is the following. So assume that we have a continuous cocycle. Note that now it is a crude cocycle. It consists of mappings of RD, and these mappings live in some metrizable separable topological group of mappings. Then this crude cocycle is indistinguishable from some perfect cocycle. So the philosophy of these theorems is that the continuous crude cocycle of mappings from some nice topological group can always be improved to satisfy the perfect cocycle property. So you can see that I'm cheating a little bit, because here I assume the crude cycle to be two-sided in time, while in our stochastic differential equations we get crude cycles for t greater or equal to 0. However, the proof for one-sided cycles is the same in the spirit, but it is more involved in different technical moments. So I will show the proof for two-sided co-cycles. Okay, now for the proof, let's consider the set M. So this is the set of all pairs S omega for which the co-cycle property holds for all t. Next, omega 0 is the set of omega such that for almost all S omega belongs to M. Here we take omega not in N0. I recall that N0 is the exceptional set for the co-cycle property at 0. In particular, omega not belonging to N0 implies that for all t, phi t plus 0, so phi t omega equals to phi t theta 0 omega, which is omega composition phi omega 0. And since mappings belong to a group, this implies that phi 0 omega is identity. Okay. So the set omega 0 is the set of such omegas such that for almost all S, this equation holds for all t. And omega 1 is the set of omega such that for almost all S, the shift of omega by theta belongs to omega 0. We will show that actually both omega 0 and omega 1 are sets of probability 1. To show this, let's look at the mapping A. So A is just the co-cycle equation, but we take the right side to the left side. Yes, so A is the composition of phi S plus t, phi S inverse, and phi t theta S omega inverse. In particular, if so S omega belongs to M, if and only if for all t, A st omega is the identity. Actually, we assume continuity of the co-cycle phi in t. So we can replace here for all t with for almost all t. Now let's note that if we take the probability that AST is not equal to identity, then this probability is less than the probability of the exceptional set NS. Because on the exceptional set NS, we have the co-cycle property for all t. And this is 0. So this probability is equal to 0 by the crude cocycle property. Of course, we can integrate it with respect to S and T and also get 0. And now we apply the Fubini theorem to integrate first in S ds, then integrate in omega, so take expectation, and then integrate in T. So we will have the Lebesgue measure of T such that A, S, T, omega is not equal to identity. And this is 0. As a consequence, for almost all pairs S and omega, the measure of this set is equal to 0, which means that almost all pairs S omega belong to M. Once again, we can apply Fubini theorem and deduce that omega 0 is of probability 1. And further, since mappings, since shifts theta preserve the probability measure, we can deduce that omega 1 is also of probability 1. In fact, so this is done by the same trick. We integrate in R the probability of the theta S minus 1 of the inverse of omega 1 of omega 0 ds, let's say complement, and this is 0. And again, by Fubini theorem, for with probability 1, almost all shifts of omega belong to omega 0. And one more property, so since omega 1 is defined in terms of shifts, actually omega 1 is invariant with respect to the shift, in the sense that if we shift omega 1, we get the same set. Okay, now we can define the modification we need. It is defined in the following way. So on the exceptional set where omega doesn't belong to omega 1, we define phi tilde as identity. Note that then we, for sure, we have the cocycle property, because if omega is not in omega 1, then shifts are also not in omega 1. So we have here identity, identity, and identity. In the case omega belongs to omega 1, we do the following. We choose any shift of omega that belongs to omega 0 and define phi tilde as such composition. So as phi t minus s evaluated at shifted omega, composition phi minus s, theta s omega minus 1. Note that this is definition of phi tilde t. So we need to check that actually this expression, this composition, is independent of S. And and such shift theta S exists because when omega belongs to omega 1, almost all shifts of omega belongs to omega 0. So we can, of course, choose one such shift. Now, to check correctness of the definition, we take omega, we take the shift that belongs to omega 0. The definition of the set omega 0 means that for almost all R and all T, we have the cocycle property for the shifted theta s omega. Yes, so we have the cocycle property in this form. It is true for almost all R. In particular, we can replace R with R minus S. Yes, so since Lebesgue measure is shift invariant, in this equation, we can replace R with R minus S, and it will also be true for almost all R. And since it is true for all T, we can replace T with T minus R and get the following equation, which is true for almost all R and all T. Okay, and now let's fix one such R. Then the composition of phi t minus r theta r and phi minus r theta r omega inverse can be written as follows. Take t equals 0 in this equation to express phi minus r theta r omega as phi minus s theta s omega composition phi r minus s theta s omega minus 1, then substitute it here and get phi t minus r theta r composition, the inverse of this mapping, so phi r minus s theta s and phi minus s theta s inverse. But note that this composition is exactly phi t minus s theta s omega. So this expression is equal to the analogous expression with R for almost all R. Yeah, so if we replace theta s omega with some other theta s prime omega from omega 0, then we can choose R the same for S and S prime and deduce that actually this mapping is independent of S. So phi tilde is well defined. Moreover, if omega belongs to omega 0 and omega 1, then omega is in omega 1, theta 0 omega is in omega 0. Yes. Hence, phi tilde is defined as phi t minus 0. Yes. Phi t minus 0 and composition phi 0 omega minus 1. We know that this is identity. So on the set of probability 1, phi and phi tilde coincide for all t. It means that they are indistinguishable. And the last thing we need to check is that phi tilde is a perfect cocycle. Why it is so? Okay, we saw that the cocycle property holds for omega not in omega 1, so we take omega belonging to omega 1. Then theta s omega also belongs to omega 1. And we take any u such that theta u omega belongs to omega 0. And note that this is equal to theta u minus s of theta s omega. Then by definition, this is phi tilde of t plus s. phi tilde of S is computed by the same expression, and phi tilde of T evaluated by theta S is defined as follows. So we must subtract exactly U minus S. Okay, so this is phi T plus S minus U, theta U omega composition, phi S minus U, theta U omega inverse. And now when we compose these two mappings, we get exactly this one. So this is, so phi tilde is a perfect cocycle overshift, and we get, in some sense, we get for free a random dynamical system from the continuous crude cocycle in the group of mappings. Now, how this can be applied to stochastic differential equations? We recall our stochastic differential equation with Lipschitz coefficients. We can construct the flow of homeomorphisms of solutions to this equation defined on the classical Wiener space. On this space, we have the shift of the trajectory of W. And if we define phi t as the mapping phi 0t, then it is a continuous crude cocycle. And it takes values in the nice group of mappings, the group of homeomorphisms. So hence, we can construct the perfect cocycle phi tilde, which is indistinguishable from phi. Using this phi tilde, we can construct mappings phi tilde st, yes, by this formula. And this will be the flow of homeomorphisms. Moreover, since phi tilde is indistinguishable from phi, phi tilde st will be indistinguishable from phi st. It means that we get a random dynamical system that generates the flow of homeomorphisms of solutions of the stochastic differential equation. Okay, in all our considerations, we had the equation driven by one Brownian motion. These results can be easily generalized to the case when we have not one Brownian motion, but some number of Brownian motions, say Bj, Wj, let's say independent Brownian motions. Nothing, so almost nothing changes in the proof of homeomorphic property, except estimates become some more complicated. In fact, one can do the same even for equations driven by infinitely many Brownian motions. To make sense of this equation, again, coefficients must be smooth enough, and for example, such condition must hold that sum of Bj squared, let's say, is finite, or supremum of x, supremum by x, so the sums of Bj squared is finite. Then such equations make sense, and all results I showed, they hold also for such equations. In particular, one can look at the equation driven by the so-called Brownian sheet, which is the space-time noise. In time, this is a Brownian motion, but we can think of the Brownian sheet as the family of correlated Brownian motions. Maybe you have already met this such equations in lectures of Professor Dorogovtsev. So if we look on the real line at the SDE driven by the Brownian sheet, and if we assume that the function beta is smooth and has L2 norm is equal to 1, we can also consider the flow of solutions to this equation. Then we have no drift here, so solutions are martingales. And if we compute the quadratic covariation, it will be computed as the double integral. So recall that for the Brownian motion, the quadratic covariation of two stochastic integrals is equal to the integral of the product dr. So here it is the same, but we integrate over two variables, dp and dr. And after the change of variables, we get such a convolution, which can be denoted by gamma evaluated at the difference of phi x and phi y. And now gamma will be a smooth characteristic function. In fact, if we take x is equal to y, we will get gamma of 0. Yeah. So if we assume that gamma of 0 is equal to 1, then we just get a quadratic variation equals to t minus s, which means that solutions of such stochastic differential equation are Brownian motions. In particular, we get a flow of solutions that consist of correlated Brownian motions. And it turned out that there are interesting, important stochastic flows, in particular, interesting and important Brownian flows, for which this characteristic function gamma is not smooth. And these flows are not defined by stochastic differential equations. Now let me give some examples of such flows. So the first general result about the existence of non-smooth Brownian flows was obtained by Harris, who proved that if we have a characteristic function which is Lipschitz outside every neighborhood of 0, then one can construct a stochastic flow that consists of Brownian motions. So in this stochastic flow, every trajectory that started at time s from point x is a Brownian motion. And the joint quadratic variation of two Brownian motions equals just the integral of the given characteristic function gamma of the difference Vx minus Vy. So there is a class of Brownian flows defined by such characteristic functions. In fact, there is one special Brownian flow that corresponds to a very non-smooth characteristic function. It corresponds to the indicator of 0. So actually, this is the discontinuous. It's not correct to say that it is a characteristic function, so it is a discontinuous positively definite function. For it, the theorem of Harris is also true, and the corresponding flow is known as the Aratia flow. In a minute, I will discuss the Aratia flow, and before that, I show the test for coalescence in the flows of Harris. So it turns out that if this integral is equal to infinity, then we get a flow of homeomorphisms, as we had in the case of solutions of stochastic differential equations. If the integral is finite, then in the flow, any two trajectories meet in a finite time. And at the meeting time, they coalesce and continue their motion as a one trajectory. So we get something like this. Let's say this is time s, time t. We have a one trajectory in the flow. We have another. They meet, yes, and then continue their motion. In particular, we don't get a flow of homeomorphisms. Yes? These flows are not one-to-one. Okay. By the way, the second condition holds for the Aratia flow, yes, since gamma is 0 almost everywhere. We can formulate the existence theorem for the Aratia flow as follows. There is a stochastic flow of random mappings of the real line, such that in this flow, every trajectory is a Brownian motion, and the quadratic covariation of two Brownian motions equals to the such quantity. So this is it is equal to 0 before trajectories meet. So tau xy is the meeting time, and it is equal to t minus tau after the meeting time. In the differential form, in this case, the differential of this expression is equal to 0, and here the differential is equal to 1. The intuitive interpretation is that before meeting, Brownian motions move independently. At the meeting time, they coalesce and move as a one Brownian motion. And this intuition is exactly what happens. So on these two pictures, on the left one, we see two trajectories in the Aratia flow. They started at time s, they have met before time t, and then they continued their motion as a one trajectory. And on the right plot, this is a realization of one random mapping from the Aratia flow. So this is the flow as a function of x. This picture means that here s less than t. Yes, this picture means that during a positive time, the flow takes all points on the real line and makes and transforms the real line into a locally finite set. So we get some random partition of the real line such that trajectories that started from same sets of partition, they coalesce and get some positions at time t. Okay. As a result, we see that coalescing flows they can be they can constitute from random mappings of that are not elements of some nice topological group. So in this case, it is not even an element of a group. Actually, such random step functions, they are not even they are not a topological semi-group. In fact, these random mappings are not even defined for all x because I didn't mention how we define these mappings at points of discontinuity. We can take the limit from the left or the limit from the right, or who knows, maybe we can take some intermediate value. And actually, this is not an easy question how to define the Aratia flow at points of discontinuity. Okay, and now I will formulate the question. No, I will not. I will show some applications of the Aratia flow. So this is indeed an important object that arises in various models. I will show two of them. The first is a voter model on integers, which can be defined as follows. So we have the Markov process of configurations on integers. So we have integer lattice, and one configuration is the displacement of zeros and ones on integers. So this process have some initial distribution depends on parameter lambda, which is the probability to choose one at every integer at time 0. And then this process evolves as follows. So at every integer, we have the rate at which the value at this integer is flipped. And the rate depends on the number of neighbors with different values. So it's like different opinions. For example, if we look at individuum that sits here, he has an opinion about 1, but both neighbors have opinions about 0. So the flip rate of this individual will be equal to 1. So here rate is equal to 1. On the other hand, the flip rate of this individual will be equal to 1/2. So he will change his mind later. If both neighbors are of the same opinion, then the flip rate is equal to 0. So this individual will not change his opinion, at least until one of his neighbors will change. Okay, and Bramson and Griffith computed the limit of the probability that in a large segment, all opinions will be the same. And it turns out that this probability has a limit when t goes to infinity, and this limit equals to the tail of some non-trivial distribution function that depends on lambda. One of motivations of Aratia was to explain this result, and he proved that after scaling, this process weakly converges to the following object. We take one mapping from the Aratia flow, so this is like a point process defined by the Aratia flow, and on each interval of a partition defined by this random mapping, we put the 1 or 0 independently according to the Bernoulli distribution with the parameter lambda. So lambda is exactly comes from the initial distribution. Okay, so the Aratia flow appears in a rather complicated way in a seemingly quite simple model. And another application is for the coalescing simple random walks. Now we have a two-dimensional integer lattice, and assume that at every point of this lattice, we have either an arrow to the right, to the upright, either we have an arrow down right. And when we defined all these arrows, we start moving along them. If we look at the motion of one, if we look at one motion, we get a simple random walk. However, from our construction, if we take two simple random walks, they will coalesce at the meeting time. What is natural to do is to scale this picture as we do in the central limit theorem, and ask what will be the limit. In fact, the limit will be the Aratia flow. It will be independent Brownian motions before meeting that coalesce at the meeting time. Again, Bramson and Griffith computed the limiting probability that in the large segment there will be no points from these simple random walks, and they obtained the limit as follows. And this limit has a very intuitive explanation in terms of the Aratia flow. Let's imagine that we have the Aratia flow, and assume that in a large, assume that in the segment of length A, there are no trajectories of the radial flow. What we can do is we can consider the so-called dual flow, which is the flow that moves backwards in time and doesn't intersect the Aratia flow. And it can be checked that this dual flow is also the flow of independent coalescing Brownian motions. And now this answer has a very good intuitive explanation. So this is the probability that backward Brownian motions have met before time t. In particular, since backward motions have met, and since the motions of the Aratia flow doesn't intersect them, we cannot have trajectories inside the segment. So this is another application of the Aratia flow. It is the limiting object for a system of coalescing simple random walks. Okay, and the question that I will address is how to generate random dynamical systems for coalescing stochastic flows. In fact, when we had an SDE, we had a Brownian motion that drives this SDE. And if you remember, we took, as a probability space, we took realizations of this driving Brownian motion, and we had a natural shift on this space. So we easily got the metric dynamical system on which random dynamical system lives. In the case of, for example, of the Aratia flow, it is not clear what to take as a metric dynamical system, because there is a very unexpected and in some sense counterintuitive result, that if we consider the filtration generated by the Aratia flow, so this is the filtration generated by mappings from times R to T, then there is no Brownian motion whose increments are adapted to this filtration. Recall that Aratia flow actually consists of Brownian motions. So if we take the mapping, let's say URT of X, then this is a Brownian motion. But if we take increments of this Brownian motion, they are not adapted to the filtration that acts between times S and T. So in some sense, we cannot cancel R here. This increment will be adapted to F RT, not ST. So the filtration generated by the Aratia flow is so-called black. By black noise, we understand filtrations that doesn't allow increments of a Brownian motion. So the first issue with coalescing flows is that it is not clear what to take as a metric dynamical system. Also, as we already noted, mappings from a coalescing flow, they may not live in a good topological semigroup. So we cannot apply the perfection procedure to get random dynamical systems. Okay, and probably I will stop here for today. And the next time we will discuss some general approaches to define stochastic flows that are not defined by stochastic differential equations. And we will also look at some results about existence of random dynamical systems for such stochastic flows and for dual stochastic flows. And so then I will stop for today. Thank you for the attention.
Okay, thank you. Or maybe some of participants have questions or some comments.
Yeah, Professor, I have a question about the first example. How do we get the environment measure of the SDE?
Okay, 1 second. This one, yes?
Yeah, yes, this example, yeah.
So we can solve the first way is to find a stationary solution of this equation. Yes, and if you substitute xt equals to, okay, if you take the initial condition exactly as this stochastic integral, then you can solve this equation with this initial condition. It is very easy to solve this equation if you compute the differential of exponent lambda t times xt. It will be equal to exponent, okay, it will be lambda xt dxt, lambda xt dt plus dxt. And this is exactly dwt. So we get e lambda t e one moment. Okay, 1 second. So if you compute the differential of exponent lambda txt, you will get e lambda t dwt. So from this, xt is equal to e minus lambda tx0 plus the integral e lambda s minus t dws. Now, if we take the initial condition as this integral, we will deduce that xt is the integral from minus infinity to t e lambda s minus t dws. All these random variables, they are identically distributed. So their distribution is the stationary distribution for the Markov process.
But how to check the invariance of this measure?
You can write the semi-group that corresponds to the Markov process. So you have PTXY, yes, integrated from -infinity to infinity with the normal distribution. Let me denote the density of normal distribution by G. It will be X, I believe X over root of 2 lambda dx. So this is the PDF of the invariant measure. This is the transition density of X. And you can just compute this integral and find that it is equal to the PDF of the invariant measure.
Okay.
This is one way, and another way is to write the equation that dpt is equal to minus lambda dx dtpt minus lambda dy pt yx, yes, plus 1/2 dty pty. Yes, so this is the backward equation for the transition density of this equation, and to find the invariant measure for this equation. So you solve for the invariant measure. You don't have the derivative in time, so you have just p double prime 1/2 p double prime equals to minus lambda p prime. I think if you solve this, if you assume that P is a probability density, you will get the invariant measure.
Okay, I will try it. Thank you.
Okay, thank you. Are there other questions? Okay, if not, then let's meet in 15 minutes for the lecture by Professor Andrei Dorogovtsov. And you have a break now. Thank you for everyone.
Thank you.